independent events. Two events, E and F, are independent if knowing the outcome of one of them does not affect the outcome of the other. In other words, the probability of E given F, knowing the outcome, let me write that down again. The probability of E given F, knowing the outcome of one of them, will not have an effect on the outcome of the other. That is, this is P of E. This is for independent events. Independent events. Knowing the outcome of one of them does not affect the outcome of the other. Likewise, the probability of F happening given that E happens. If E and F are independent, knowing that E happened does not affect the probability of F happening. It's just simply P of F. Knowing the outcome of one does not affect the outcome of the other. We could say, or our textbook can say, that what I just boxed is the definition of independence. But we can come up with a cleaner one. Let me write this down again, and we'll do some very basic math. First, I'll use the definition for this one. This is P of E intersect F divided by the probability of that one. And I'm not going to touch the right-hand side. Just keep in mind that this is a number. It's between 0 and 1. This is a number, and this is a number, and of course that's an equal sign. You can always multiply the bottom times the other side and say it equals to the numerator. Multiply 2, I'll write E first. P of E times P of F is equal to the numerator. P of E and F, or if you prefer, P of E intersect F. This here is the definition of independence. It's the same as that line on top. These two are equivalent. E and F are independent if when you multiply P of E by P of F, you happen to get the same answer as P of E intersect F. If events are not independent, that equal sign will not be valid. If events are independent, then the equal sign will be valid. If two events are not independent, they are said to be dependent. Usually you're asked if two events are independent. And if that rule or test fails, then you say no. But let's try to motivate this. Suppose you toss a coin and then you roll a die. You toss a coin, then you roll a die. What's the probability that the toss of the die is 6, given that the flip of the coin is a head? Now, think about it. You toss a coin, and you roll a die. Do you really think the outcome of the toss of the coin is going to affect how the roll of the die? The answer is, of course not. That this is just going to equal the probability that the die is 6, which is 1 out of 6. But let's actually do it the long way. This is the probability that the die is a 6, and the toss of the coin is a head. That is, you get a 6 and a head, divided by the probability of getting a head. Well, I'll jump on that one. the probability of getting a head is a half. Now, what is the probability of getting a 6 and a head? Well, there are two results. The 6, the toss of a die, there's 6 outcomes. And then you toss the coin, there's 2 outcomes. If you want to say, well, first you said toss the coin, there's 2 outcomes, and then roll the die, which has 6 outcomes, you're right. It is 12 it's out of 12, and that's only one outcome. A 6 and a head is only one outcome. It's 1 out of 12. And this is 1 out of 12. Keep the numerator the same. Change division to multiplication and flip over the bottom. 2 over 1. 2 goes into a top number and a bottom number 1 time and 6 times. 1 times 1, 6 times 1. It's a sixth. We got the same answer. We got the same answer as we did before. They are independent. Now, let us show this using the definition of independent. Let us show this using the definition of independent. So we need 2 events. Event 1, which I'll call E, is you got a 6 on the die. You rolled the die, you got a 6. And event F is you flip a coin and you get a hit. Okay. So to find out if E and F are independent, you have to first find P of E, or you have to find P of E, P of F, and P of E intersect F. You can find those 3 in any order you want. Since there's 3 of them, you could do them in 6 different ways, in 6 different orders. I don't care which one you do first, which one you do second. Just make sure you do all 3 of them. The probability of E, the probability that you toss a coin and you get a 6. 6 possible results when you toss a die, and one of them results in a 6. What's the probability that you flip a coin and you get a head? Well, there are 2 outcomes. One of them is a head. What's the probability that you roll a 6 and toss a head? Well, we talked about how there were 12 outcomes. 6 for the die and then 2 for the coin. And exactly one of those 12 will be a 6 and a head. Like if you were going to record this, you might record a 1 and a head, or a 1 and a tail, or a 2 and a head, and then a 2 and a tail. You might have recorded a 3 and a head, and if you're the one rolling it, you might have, or doing this experiment, you may have rolled a 3 and tossed a head, or rolled a 4 and, I meant to say tail, roll a 4 and toss their head, roll a 4, tail, roll a 5 and then her head, or a 5 and then her tail, or a 6 and then her head, or a 6 and then her tail. If somebody asks you to record the results of tossing a die and then flipping a coin, these are the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 things you might write down. Okay, and exactly one of them is a 6 and a head. So that's why I put 1 over 12 here. Now we're ready to decide. Well, let me use more space. Now that we have those 3 probabilities at the bottom left corner, we need to know what to do with them. And we want to decide if P of E times P of F, does it equal to P of E intersect F? Okay, we don't know yet. Does P of E times P of F equal P of E intersect F? Well, P of E is a sixth times P of F is a half, and P of E intersect F is a twelfth. Are they equal? If the answer is yes, we say independent. If the answer is no, we say dependent. Well, 1 times 1 is 1. 6 times 2 is 12. And of course, 1 over 12 equals 1 over 12. So E and F are, in fact, independent. Knowing the result of the toss of a coin will not affect the roll of a die. Okay, knowing what you got for the roll of the die is not going to affect the flip of the coin, and vice versa. One does not affect the other. Knowing the outcome of one will not affect the outcome of the other. Suppose you flip 2 coins. Do a very similar one. Flipped 2 coins. E is an event that the first lands on tails. And F is the second coin lands on, say, heads. And we want to know, are E and F independent? Are E and F independent? In fact, of course the answer is yes, and because, again, knowing the result of one coin will not affect the result of the other. How about I say, show this. Give me a rigorous proof. Oh, you want me to show E and F are independent? I'm going to find P of E. I'm going to find P of F. I'm going to find P of E intersect F. And then I'm going to decide if P of E times P of F, does it really equal to the probability of E intersect F? Well, probability of E, the probability that the first coin lands on or tail, it's 1 out of 2. The probability that the second coin lands on heads, 1 out of 2. The probability the first is tails and the second heads, well, when you toss 2 coins, you can get tail, tail, first a tail and then a head, first a head and then a tail, first a head and then a head. There are 4 outcomes equally likely, and only one of them has tail first and head second. It's a quarter. Okay, now our test. P of E, looking at the left here, is a half times P of F, which is also a half. Does that equal to P of E intersect F, which is a quarter? Well, 1 times 1 is 1. 2 times 2 is 4. And of course, a quarter equals a quarter. So E, well, okay, yeah, so I'll say it. So E and F are independent. So we proved it. We showed that it really is true. You need to show that this equals that. That's all. Okay, lots and lots of students, they just don't get that concept. You need to show those. I know lots and lots of probability students who can find P of E, can find P of F easily, can find P of E intersect F. But for some reason, they can't do this part, and since they're equal, conclude that they are independent. Don't be one of them. You just need to show that those 2 quantities are equal. P of E times P of F is equal to P of E intersect F. Or that they're not equal. They're not equal, you say that they are dependent. Okay. Do another dice problem. Toss 2 dice. And E represents the sum is 7. And F represents the first die is a 4. The first die is a 4. I want to know if these two events are independent or not. Okay, so the probability of E, the probability that the sum is 7. Well, there are 36 different outcomes. When you toss 2 dice, how many of them are 7? Well, you have 1 and 6, and 2 and 5, and 3 and 4, and a 4 and then a 3, and first a 5 and then a 2, and a 1. That's the first one. Oh, it says 1. That's the second one. Look at that. It says 2. Look, that's the third one, and it says 3. Oh, that's the sixth one. That is, there are 6 of them. 6 goes into 6 one time, and into 36 6 times. So the probability that when you toss 2 dice, the sum is 7, is 1 out of 6. The probability of F, the probability that the first die is a 4, it's 1 out of 6. Now, what is the probability of E and F? Well, 1 die is a 4. You're tossing 2 dice. The first one is a 4, but the sum is a 7. Well, that means the first is 4, and the second is a 3. We have to have the first being 4, and if the sum, that's this one, and for the sum to be 7, that means the second has to be 3. You toss 2 dice, there are 36 outcomes. Of those 36 outcomes, how many have a 4 first and a 3 second? Just one of them. So now we have the information that we need to make the decision, the determination, if these two events are independent or not. Is the probability of E times the probability of F, does it equal to the probability of E intersect F? Well, the probability of E is a 6th, the probability of F is a 6th, the probability of E intersect F is 1 over 36. Where did I get that from? From my calculations down here. 1 times 1 is 1. 6 times 6 is 36. Does that equal to 1 over 36? Of course it does. Of course it does. So in fact, E and F are independent. They are independent. Now sometimes you just can't look at a problem and say, yeah, independent, or no, not independent, that is dependent. When you get good, better, you can do those things more frequently. Let's look at a very, very similar problem. Toss 2 dice. Toss 2 dice. E is the event, the sum is 6. And F is the event that the first roll or toss of the die is 3. Okay. Question is, are E and F independent or not? Well, let's go by the rolls. P of E is the probability of the sum is 6. Well, it's out of 36 to get a 6. You can have a 1 and a 5, or a 2 and a 4, a first a 3 and then a 3, a 4 and then a 2, a 5 and a 1, but you can't get 6 in anything. So there are 5. So it is 5 out of 36 that you will have a sum equaling 6. The probability of F, the probability of the first toss of the 6, well, that's 1 out of 6. Now, what about the probability that the sum is 6 and the first is a 3? Well, the first, if the sum is a 6, the second has to be a 3. First is a 3, second is a 3. That's 1 out of the 36 different outcomes. Okay? Once you have this, you're 90% there. Don't stop. The probability of E times the probability of F. Does it equal to the probability of E intersect F? You see it does or it doesn't. Get your hands dirty. Decide. P of E, 5 over 36. P of F, 1 over 6. The right side, 1 out of 36. Well, if these canceled out, you'd be in business. But this is 5 out of 216. And it does not equal to 1 over 36. So in this case, E and F are not independent or dependent. Let's see. The probability of F given E. Does this just equal to the probability of F? I mean, the answer is no, because we just proved it. But how can we see this? No, I want to do it the other way. The probability of E given F. The probability of E given F. Okay. What's the probability of E given F? Well, the thing is, if F is a 6, if F is, the first is a 6, then the probability of E given F will be 0. Because if the first is a 6, then there's no chance on E happening. But if the first is a 1 or 2 or 3 or 4 or 5, that second row can end up having the sum being 6. Knowing what the first toss is has an effect. Knowing what the first toss is has an effect. Notice I didn't stress the fact that F was first is 3. Just knowing the result of the first, in this case, had an effect. Why didn't it have an effect when the sum was 7? Because no matter what you got on the first toss, that second toss could have summed up to a 7. Whether you got a 1 on the first toss, or a 2, or a 3, all the way up to a 6. You were still alive. You still had a chance. But if the sum is a 6, the sum is 6, there are some first tosses that will knock you out. You don't even bother doing the second toss. So, if you can see that and see that on your own, excellent. Your teacher should be very happy if in this last problem You actually stated what I said at the end. These two events are independent because, for example, if you got a 6 on the first toss, the probability of the sum equaling 6, given that the first is the 6, is going to be different, it equals 0, it's going to be different than if you got the first toss being a 4, or a 3, or a 5. It does matter. Okay, so those are two nice problems. Now, here's one. It's not a problem, but it's a proof. The results are interesting. Theorem. If E and F are independent, then so are E and F complement. And the probability course, you should be given proofs to do. And this is one of them. Okay. So let's write down what we're given and what we're asking. E and F and what it means. E and F independent, that implies that P of E intersect F is equal to P of E times P of F. E and F independent implies that. Okay, this we have. What do we want? We want E and F complement independent, which implies P of E intersect FC is equal to P of E times P of F. Or P of E given F complement is equal to P of just E. Or if I switch it, P of F complement given E is just P of F complement. The given parts don't matter if they're independent. Okay. All right. So, what would I do in this case? All right. So, you know what? I see E's, and I see both F and F complement. That really gets me to always think this. E is equal to the union of these two disjoint sets. E and F, or E and not F. I'm going to take the probability of both sides. The probability of E is equal to the probability of the right side. But since it's a disjoint union, this set and this set have nothing in common. And after all, to be in here, you have to be an F complement. That is, you can't be an F. And to be in here, you have to be an F. Okay, so I can just add them. It's P of E intersect F plus P of E intersect F complement. And then I'm going to use the property that I know. Since E and F are independent, this is P of E times P of F plus this. I'm going to solve this equation for this. That is, I'm just going to bring this piece to the other side. It's going to become P of E minus P of E times P of F, and it's going to equal this. P of E and F complement. But this right-hand side, there's an understood one here. Between here And here, they both have P of E. I can factor that out. And what's left over is 1. But here's the beauty. 1 minus P of F, well, I just wrote down P of E. 1 minus P of F is P of F complement. That is, this is equal to that. That's the definition of two sets being independent. P of this set intersect that set should equal to P of this set times P of that set. This was E, that set was F complement, this set was E. So it is true. It's a very, very nice problem to put on a test. Of course, I would have nothing against you writing this on an exam, anything that helps you to think, but what I just put in red is not needed. Okay, the proof is right here. And of course, I showed this one. Actually, the implication goes both ways. They mean the same thing. Okay, so that's nice. So, you were given that E and F was independent. That means knowing that F happened doesn't affect the chances that E happens. You know what? Knowing that F didn't happen doesn't affect the chances that E happens. Okay? Knowing anything about F, it did happen, it didn't happen, doesn't matter. It doesn't affect E. Now, here's an interesting problem. Let me state what we notice in the conclusion. So, if E and F are independent and F and G are independent, then E and F intersect G does not have to be independent. Now, let's see if I can come up with an example. All right, here it goes. You toss 2 coins. And E is, the sum is 7. And F is, the sum is 4. No, sorry. The result of the first toss is 4. First toss is 4. And G, the second is 3. The second toss is 3. Now, we know that those two are independent. Actually, yeah, we do know that from the last problem. And now, so this one is independent. And I claim that F and G are independent. Now, just for the record, first of all, this has nothing to do with the problem. Okay, so 2 things. Show that F and G are independent, and B, that E and F intersect G, that's one set, are independent. Well, to show that F and G are independent, well, the probability of F, the probability of G we need to know, the probability of F and G we need to know. The probability of F, the first toss is a 4. That's 1 out of 6. The second toss is a 3. It's also 1 out of 6. You may say, but wait a minute, you're immediately assuming the first toss didn't matter. Fair enough. You can have a 1 and a 3. Notice the second is a 3. You can have a 2 and then a 3, a 3 and then a 3. The first can be a 4 and then a 3, a 5 and a 3, and a 6 and a 3. So basically, there's 6 favorable outcomes out of 36. But you know what? That equals 1 over 36. That reduces to 1 over 36. Six out of 36 is a 6. Now, the probability of F and G. The probability of F and G. Well, isn't that the probability of E? The probability that the sum is a 7? If the first is a 4 and the second is a 3, sum is 7. And out of the 36, 6 of them give you a 7. Make believe these 6s, these 3s were all 6s. There are 6 ways of getting a 7. And those aren't them, excuse me. You know, 1 and a 6, a 2 and a 5, or 3 and a 4, a 4 and a 3, a 5 and a 2, and a 6 and a 1. There are 6 different ways. This is 1 out of 6. Okay. Actually, it may not be true. The question is, are F and G independent? Are E and F independent? Okay, so the first part, you multiply P of F, P of G. P of F times P of G. Does it equal to P of F and G? Answer is no. A 6 times the 6, does it equal to a 6? No. 1 over 36 does not equal to 1 over 6. You get one problem right on an exam, and you take 2 exams. You keep getting only 1 right. You get 1 right out of 36 and 1 right out of 6. Those are 2 different results. Okay, so the answer to part A is no. Now, what about E and F intersect G? What about E and F intersect G? Let us get a little bit more room going. We'll try to use the information that we learned from part A. When we do stuff, we already have the answer. So, the probability of E and the probability of F intersect G. Okay. Then we'll do this second part a different way. The probability of E, we worked out. The probability of the sum is 7 is 1/6. And we actually concluded that P of F intersect G is the probability of E, which is a 6. Now, what is the probability of E intersect F intersect G? Now remember, F intersect G is just E. What's the probability of E intersect, well, what is E intersect E? It's E. Probability of E is a 6. And this is where it falls apart. The probability of E times the probability of F intersect G, does it equal to the probability of E intersect F intersect G? Well, this probability is a sixth times this probability is also a sixth, and this probability is also a sixth. 1 over 36 does not equal to 1 over 6. Okay, so no, this set and this set are not independent. Are these independent? Answer, no. Okay, but I also mentioned that you can see it. Remember, the probability of E given F intersect G, if it doesn't equal to P of E, we're in trouble. Now, remember, that's E. You are given that E happened. You are given that you got a 4 and a 3. You're given the sum is 7. What's the probability that E happens given that E happened? The answer is 1. This does not equal the probability of E. The probability that the sum is 7 is not certain. That would be enough. That would be enough. If you wrote, for part B, if you wrote down this part, you said that this conditional probability is equal to the number 1, which is not P of E, I'd give you full credit for that. That really means you're thinking. There's nothing wrong with thinking. Okay, that completes the section on independent 6.